and concurrent mark and sweep and move them together and be at the best of all worlds. And it was a great step in the right direction. However, it still stops the world, stops all the threads to do the copying of objects. So all Shenandoah is that we're going to copy the objects while your program is running. That's it. Okay, so I know you guys all care about end-to-end runtime, and so I need to be absolutely honest and straightforward here. Shenandoah is all about shorter pause times. There's no such thing as a free lunch. It's going to impact the end-to-end runtime. And I'm going to tell you about why as I go along. So let me say, what do you mean by ultra-low pause time? Okay, so Shenandoah is not pauseless. It could be pauseless. We have plans to make it pauseless. But for now, the first step is just doing concurrent evacuation. And I came up with these numbers. I pulled these numbers out of my head. 10 millisecond pause times for 100 gigabyte plus heaps, because that makes people happy that are just listening to numbers. The reality is, if you have 1,000 threads and they all have really big stacks, you're not going to hit the 10 millisecond pause time. At least not in the current Shenandoah. Maybe later on when we get to the Shenandoah 2.0. So why not pauseless? It's harder. It's one thing to get your brain out of moving objects out from under the running Java program. It's another thing about keeping the graph consistent while only stopping one thread at a time. And so we're taking one step at a time. I'm going fast, so if you want to interrupt me with questions because I'm going too fast, please do, because I get nervous and I talk quickly. What exactly is it that the GC is organizing? I wasn't sure of my audience for my talk, so bear with me. In a Java program or a lot of object-oriented programs, you have stack frames. So here we have 2 stack frames for foo and bar. And then they have immediate values like 42 and 6.847, but they also have references to objects that are allocated in the heap. So arrays and objects. And as you can see, some of these objects are referenced by more than one stack, and some of these objects are referenced by stack frames and by other objects. And some of these objects, like the one, I'm pointing at my screen and you can't see it, some of these objects, like the bottom right, are not referenced by anybody. So all that garbage collection is doing is going through, finding the objects that are pointed to, that you can get to, compacting them into an area of memory so that you've got better cache line behavior, and freeing up space for you to allocate new objects. That's all GC is. It's simple stuff. What the heck? I can just get up here and talk. My slides would have been a big help, but I need to be able to recover. So what is the big trick for doing concurrent garbage collection? The big trick is to move the objects while the program is running. And what's the trick for that? You need the compiler and the runtime system to agree on where an object lives. So you can do that in one of 2 ways. You can take the way that another company has done, where they memory protect the pages. And then whenever you hit one of those pages, you take a trap and you copy everything to 2 space and you keep going. Or you can take the strategy that we took. We're back. Thank you so much. I really am competent with computers, I promise. I'm just nervous. All right, we're going to have to go fast. All right, so the reason concurrent compaction is hard is because you have references from your stack frames and from your heap to point to this object. And everyone has to agree at the same time where that object lives. And so you can do that via memory protection, where you stop, you go through your memories, your remembered set, and you fix all those things up. Or you can do what we did, which I'll get to in a minute. So let's talk a little bit about what GC does. It walks the stack, it traces the live objects, and it copies objects. So all of the current GCs do the tracing of the live object concurrently while your program is running. What we do is we do the tracing of the live objects and the copying. I'm going to have to speed up a little bit. Shenandoah 2.0 is the one that's going to stop and walk the stack frames while the program is running. So what do we do to make the pause time shorter? We only collect part of the heap at one time. There's no point to touch long-lived data that isn't changing. We use multiple processors to GC faster, both for concurrent marking and concurrent evacuation. And we do GC work while the program is running. So what does Shenandoah do to we divide the heap into regions. We run a concurrent mark step over your heap so that we know where all the live objects are. This is both so we know which regions we want to garbage collect. We can pick the pretty regions that have very little live data. We can also know which objects are live and need to be evacuated when it's time to copy them.
So it's a copying collector?
It is a copying collector. That's what I meant by concurrent evacuation. We copy while the program's running. So here you can see that, we picked the 2 regions that were the most garbagey, and we copied them over to a 2 region and freed those regions up. So just to show you what I'm going to use for the rest of the talk now that I have slides, we pick a collection set like those 2 regions that were garbagey, and we compress them into one other region. And then when we're done, these 2 blue regions are the free regions that are left after we've done that. So the targeted regions are red, the 2 regions are green, and there you go. So what's our trick? Our trick is, well, I have 2 jokes here, but since they're falling flat, I'm just going to tell you they're forwarding pointers. The first trick, my first joke was that we stole something from 1984, right? We took the Brooks forwarding pointers and we revamped them to work in today's systems. My other joke is that we added a level of indirection, which is how you solve any hard problem in computer science. So all of your accesses go through a forwarding pointer to find the real location of the object. Now, I know everybody's sitting there and they've got 2 things that they're afraid of. One is, oh my gosh, that's a space overhead, and oh my gosh, that's a time overhead. So depending on the size of your objects, it can be a space overhead, right? If your program is all forward long objects, then it's a 25% space overhead. But I don't think the programs we're looking at are not all small objects. In terms of time overhead, I'm not going to tell you where we are now, but I will tell you I will tell you why we aren't where we want to be in a few minutes. But there are papers out there that show that an unconditional read barrier can only cost you approximately 5% in terms of throughput. So just to be absolutely clear about how this works, your foo pointer points to A, which is in a from region. The garbage collector comes along, it copies A, installs the forwarding pointer, and whenever anybody comes through foo to access A, they actually go through the indirection pointer before they can read, if they read the final object. So one of the added benefits to this technique is that we no longer have remembered sets. In the generational collector, you have a card table remembered set, and that can be a concurrency bottleneck because people are writing to the card table from disparity areas of the heap. In G1, the remembered sets can get big. In original G1, they were a real problem. In generational G1, that got better, and I'll talk about that too as we go along. But the idea here is that we no longer have remembered sets. We're no longer hiding it, right? You have the overhead of this one word per object. All right, so here is a nice picture of what Shenandoah actually does. So let me see if I can get over there. Given how well I'm doing, I might trip. So your Java threads are running. You've got all this concurrency. Life is good. We're going to stop the world to do an init mark. What that means is we're going to trace the roots and find out what the roots point to so we know where to start. We're going to start the Java threads up again, and we're going to do our concurrent mark while your threads are running. We're going to stop again and do a final mark to make sure that we've got the correct graph. We're also going to do the evacuation of the things the roots point to there. And then we're going to start your Java threads up again, and we're going to do a concurrent evacuation. Now, one thing that the astute observer might notice is that I haven't actually talked about where it is that we clean up references. You have references to the heap that point into from space, and that's actually a point of contention between Roman and myself that we've been working on it. If you have plenty of space and all you care about is pause times, you can wait until the next initial mark, and when you go through there, you can clean up all the references. If you're willing to take another short pause, you can start another concurrent phase that cleans up all the references. So concurrent marking uses a technique called snapshot at the beginning. Anything that was live at the start of concurrent marking is still considered live. Anything that was allocated since the start of concurrent marking is considered live. So we use this to update references in my world. You can do either way, it's a command line option. You can keep track of the amount of live data for each region, and you can tell which objects are live and need to be evacuated. Now, one of the tricks about SATB to get it to work right is that you need to keep your copy of your graph consistent. So in this case, I have X pointing to Y. Sometime during marking, An object that's already been marked will get written with Y, and then X will get rewritten with W. If we didn't have some sort of a write barrier in place, we would miss Y and Y would not get marked. So that's the first part of our write barrier, is making sure that Y gets marked. So how do we move an object while the program is running? It's basically the same thing we did for parallel young-gen, except instead of just competing with other threads, we're now competing with the Java threads as well. So we read the forwarding pointer, we allocate a temporary copy over in 2-space, we speculatively copy the data over, and we cast the forwarding pointer to the new copy. If we succeeded, we carry on. If we failed, we roll back the thing we allocated in our thread local allocation buffer, so we can just go back, and we keep going. So reads. We allow you to read in the from region. This is one of the things that I think is a benefit of Shenandoah over the protected memory barrier version. If you have a protected memory barrier, then all reads have to generate evacuations. So when you get to a flip, you can have a read storm where everybody's trying very hard to copy stuff over and your Java threads aren't making progress. In our case, we don't have to copy on reads. So your Java program that's going can keep doing reads. In fact, we can be even a little bit more clever in that if you're reading the size of an array, we don't even put in an array barrier. If you're reading a final field, we don't put in a read barrier. If your final fields are getting changed under the covers by ASM, that's your own fault and not my problem. Good, let's do what the language intended. Writing triggers a write barrier, and our write barriers are more complicated, right? The write barriers for SATB, like I just described, are only triggered when you're writing a reference. Our write barriers have to be triggered whether you're writing an int or a reference or anything, and we're doing the SATB barriers, but we're also doing a copy on write. And the reason for that is if we allowed you to write into from space while the garbage collector was copying objects, there's the potential for those writes to get lost. So we force the Java thread to copy the object and then keep going, and it can do its writes in the 2-space, and then any thread that later comes along can see that. There is a race window between a reader and a writer, but that's a race window that would be there anyway. So the invariant is you're never allowed to write into from regions. The other bit of knowledge that we came across is that you have to write 2-space copies. So you can't write a pointer to the from space into the 2-space. It's a little, if you're familiar with garbage collection research, it's a little weird because we're doing snapshot at the beginning for concurrent marking, we're doing incremental update for our evacuation, but it's what works for us now. And if I hadn't said it before, let me say it now. This is a project in development. This is not a product. I mean, you can download it, you can play with it, you can contribute, but it's not really ready for your primetime production system yet. Okay, one of the things that I wasn't anticipating, and that Baker didn't anticipate in his paper, is what happens when you CAS, right? CAS is complicated because you're comparing and swapping. You have A that has an object reference X, and you want to move it from foo to bar. Well, you can lose if foo hasn't been copied yet. So one of the things that's a downside to Shenandoah that is a problem that we need to address, maybe, or maybe it won't be a problem because uncontended CASs are cheap, is that in order to do a CAS, you have to copy all of your objects to 2-space before you try and do the CAS. So what would be a one CAS instruction has the potential, if all 3 objects are in a targeted region for evacuation. If you remember my slide back before, that's not all of them, that's only some of them. But if it is a targeted region, then we have the CASs to move the object to 2-space, and then the CAS. This is just showing the copying of the objects. So does this mean that a write could keep a Java thread from making progress for an unbounded amount of time? No. I mean, at the worst case is the CAS where you have to copy 3 objects. And objects are limited in size to a heap region, which is settable on the command line, how big it is. Objects larger than a heap region are what we call humongous and are treated separately, and they never get copied. We use multiple threads. We use what we learned when we did parallel garbage collection with work stealing. So as many processors as you have left over that you aren't using, we can use to get the garbage collection done faster. And this is just a demonstration of work stealing where when you have an undisciplined graph like you do in an object graph, it works very well for work stealing. You compete to claim the roots, And then as you're tracing them, you do one child and you put the other children on a list for later. And you can quickly see here that all these other threads got in to compete and are all helping to do whatever this is, whether it's concurrent marking or parallel evacuation. Although actually the concurrent evacuation doesn't use quite the same thing, but it is all done in parallel. So the cost, space, it's an extra word per object. It can be expensive if you have a lot of small objects. It is the case that words in the JVM are double word aligned. So we're hoping that eventually down the line, when we're doing real performance tuning, there might be cases where we can save that extra word by just sticking it in an unused word in an object. Time, we have read barriers. No other garbage collectors on the JVM have a read barrier in OpenJDK as it is now. And our write barriers are more complicated. This is why I'm saying you're going to lose some % of time in throughput. However, if what you really need is ultra low pause times, if having your application go away during a stock trading window, or if you have to meet a quality of service deadline, or you want an interactive application and you can't afford a 1 minute pause time, maybe you're willing to pay 10% or 5% to get Shenandoah running. So as I said, our read barriers are unconditional. Our write barriers, we need the SATP write barrier, and we also need write barrier on all writes, even the writes of integers and such. So what's our current status? We have something working. You can go and download it, you can run it. We can pass small tests like spec JVM and spec JVB. We have passed the smoke test for some applications like Eclipse and Thermostat. We're working on performance tuning. Right now we have Radar Gun and Elasticsearch, but I'm putting out a call to all of you. If you have an open source application that you think would benefit from a low or no pause garbage collector, share it with me. We'll test on it, we'll make sure it works, we'll do performance tuning on it so you get something back out of it too. We'd love to have that. So performance tuning, so let me talk a little bit about that. One of the things that is kind of an open research issue for us is what the heuristics should be. When do you start a concurrent marking? How large should the collection set be? How many bytes do you allocate before you do this? How full does the heap region have to be to qualify for the collection set? We think that's going to make a big difference once we get it right. We've thrown some darts at dartboards to do our best shot. Now, I know you guys are going to want preliminary results, and I'm really not in a position to give them, but I'm going to give you a little bit of what I can. In spec JVM, the only one that actually does significant garbage collection work is spec JVM compiler. It's not our target application. It doesn't have a 100 gigabyte heap. We're just starting performance tuning. I thought we'd be further along when I volunteered to do this talk. But I can show you that we have initial mark times in the 5 to 8 milliseconds for initial mark and final mark. Our max times are 10 to 15 milliseconds, which isn't where we want, but it's good. If you compare these to G1 with 31 milliseconds and 75 milliseconds, it's looking a lot better. I had to include the references because, to be honest, all we did was we took the work of Baker and the work of G1 and we put it together, and we're making it work. Future work. I love this section. I can say all the things that I wish I could do. We're going to finish basic application testing, and we're working really hard on that. We've got Radar Gun working. We're working on getting Lucene and Elasticsearch working. There's still some issues. Where our performance bugaboo is, okay, true confessions time. When we went to put the read barriers into C2, I don't know if any of you have ever looked at C2 in the JVM. It's an optimizing compiler that only the very brave fear to tread in. So we put our read barriers in at parse time because it was the easiest time to figure out where they go. Unfortunately, what we didn't foresee was that a bunch of compiler optimizations don't get triggered because they don't match what they were expecting to see in the nodes. So we have seen things like loop optimization elimination not happening. Loop bounds checking elimination not happening. So our goal is to take the read barriers out of parsing and to put them in right before code generation. And we think that's going to get us a lot of the performance back. And when I say performance, right, we want to be within 10%. We're actually at a factor of 2. The absolute worst I saw was a factor of 8 once, but that was an anomaly. I think that once we get C2 generating as good a code for Shenandoah as it does for code without read barriers, with adding the read barriers, I think we should be within the 5%. That's what studies have shown that a read barrier will cost. Heuristics tuning, like I talked about. One of the things that I really want to explore is whether or not the generational hypothesis on its own makes sense. If you're familiar with generational garbage collection, there are people that say that the benefit to generational garbage collection is not that your objects die young, but that your remembered sets are smaller. Because it's very frequent that you have new objects that point to old objects, but you rarely have old objects that point into new objects. So the remembered set, to be able to collect the young generation individually, is smaller than if you had any other remembered set, like in G1. So my hypothesis is that we don't need to be generational because we don't have a remembered set. But we aren't really there yet. We haven't gotten to the point to test that. And maybe we want to be generational. Maybe we want to even have a remembered set. Maybe we want to add an Eden. Like I said, this is a project in progress. It's not done. We definitely want to get to round-robin thread stopping. We want to be able to say we're really pauseless. And one of the other things that's on our list to maybe look at is G1 or Shenandoah lend itself really well to NUMA awareness. And particularly working for Red Hat, where I have the kernel guys sitting next to me, I have access to the folks that know how that stuff works, and we can probably get something going where we could have a NUMA-aware garbage collector, not just in the allocation area, which other people have done, but also as your threads move around, the data can follow them. If you need more information, or if you want to download the code, you can download it from this URL. I have a blog. It's a little out to date. Roman has a blog too. His is better. Or you can send us email. And I'm hoping that somebody has questions because I rushed through this. So does anybody have any questions? Thank you. If you could please stand up and ask your question. Yeah.
So the forwarding pointers, suppose that you cached a reference in a register or local variable. Do you have to follow the forwarding pointer each time to reload it?
Okay, maybe I should have talked about save points. At save points in the compiler, you are... Okay, the question is that compilers do nasty things, like keep pointers into the middle of arrays and such. And do we need to go through on every read to make sure that we go through the forwarding pointer? And the answer is we don't. When you are at a save point, as long as you only have to do it potentially once per save point, but really, if you read the Java memory model, and if I want to hide behind it, you don't even have to do it then. You only have to do it after any instruction that would cause a sink, a memory sink. And in those cases, then you have to go and redo all your read barriers. Are there any other questions? Yes, you.
Do you have a minimum Java version that Shenandoah is targeted towards, like Java 7 or Java 8?
We are working in the Java 8 code base. So if you download Shenandoah, you get Java 8. We have a JEP in place, and I'm going out to Java 1 in 2 weeks. And hopefully I will figure out how we go about seeing if we can get this put back upstream into Oracle. I don't know how that works. I mean, having worked for Oracle, I don't know how it works from the outside, and so we're trying to figure that out to navigate that process. And even if we can, I don't know if we can. Yes?
What are remembered sets and how are they implemented in some other examples?
Okay, so if you have a generational collector with a young gen and an old gen, what you have is you have a card table. And so every time you do a write, you put a little bit in the card table that says, hey guys, when you do your young generation collection, I want you to come and scan this card in the old generation, because there's a reference there to the young generation, and if you move something, you have to update this piece of the old generation.
So how does G1 handle card scanning? I know in CMS it's very time consuming.
Okay, in G1, I can tell you how G1 originally did it. So back when I was working on G1 in the dark ages, we had a full remembered set and into remembered set. So any card anywhere in the system that it pointed into a particular region was kept in a region remembered set. And since then, they've made generational G1 so that you don't have to keep pointers from old to young, because that's handled by the card table. And they've also done some remembered set coarsening. And I'm not up to speed on exactly what that is.
My question is specifically, so like card scanning time, if you have a large old generation, then the card scanning time is significant.
At least in G1 and in CMS, they both have, one is called a concurrent refinement thread, and I don't remember what the other one is, but they both have a concurrent thing that goes along across the card table and figures out what needs, if they can do any cleaning concurrently before you actually have to start doing a stop the world pause.
Okay. I have a slide I'm showing tomorrow that sort of says the opposite, which is as you increase the size of an empty old generation, my young Gen GCs just got larger. I assume that was card scanning, but I should probably have had that log.
The card scanning is really quick. And I'm trying to remember exactly how it does. See, I haven't looked at that in 2 years because we don't have a card table. Yes, you and the tie-dye. Love tie-dye.
I have a super basic question about read barrier. So you're talking about optimizing the compiler and how there was a problem with like the loop invariant. So does this mean that to make the garbage collector work, you have to change the compiler?
We are trying very, very hard. Yes, we have put read barriers into the interpreter. We have put read barriers into the server, the client compiler. And the client compiler you can understand. It's like a Dragon Book compiler, and you can figure out, okay, this is what I need to do.
What's the client compiler?
When you run in a tiered compilation on Hotspot, you run interpreted, and once you hit a threshold, you run with the client compiler, which is sort of, think of it as a fast and dirty compiler. And when you've been running for a longer amount of time, you hit C2, which is the optimizing compiler, which is I'm willing to take a little more time to do this compilation for code that's faster to execute. And that one is black magic. And that's the one that our read barriers tripped up, in that it's looking for particular instructions sort of in an instruction window. And because we added a read barrier there, it didn't recognize it as what it's used to optimizing. And we honestly, I've tried, I really have. I've tried to penetrate C2, and it's very tough. And it seems like our best course of action for our next try is, rather than doing them in parse time, now that we have them in parse time and we've proven the theory that it all works, is to go back and put them right up before machine generation. Because we can see where that is. We can tag the nodes, and we know these are the nodes that we're going to have barriers on. And, well, hopefully we can tag the nodes and know those, whether C2 generates new nodes for us. We're going to have to figure that out as we go along. And then put them at the end. And hopefully then we'll have gotten all the compiler optimizations in the middle end. Compiler optimizations will work for us. Yes?
What are the general strategies to ensure correctness or to give you read that this all works?
We're hoping that we're based on sound theory. The question was, how do we have confidence that this all works? It's an awesome question, and we're based on good theory, right? I think that the idea is to publish a paper and make sure that other people get to see it and that other people agree that we're based on a sound theory. We're doing a lot of testing. We've passed all of the TCK, which wasn't hard for a garbage collector, but the compiler folks were impressed that we passed it the first time. We're running big apps that run for long periods of time. We also have something, we stole the memory protection trick, and we use that for verification. So we verify that you never write to from space. We have other kinds of verification like that. We're doing the best we can to prove that it's correct. I'm pretty sure that none of the garbage collectors in OpenJDK are perfect. But I think that we can do well. I think that we can do a pretty sound job. Yes.
One of the problems with G1 we've seen is that it disables some of the hotspot optimizations. Do you have any comments on the impact on the optimizing compiler? Like, are there certain optimizations that are no longer valid in Shenandoah? Or could we see improvements versus G1?
If you can name a specific optimization to me, I will go and research it. I don't know of any optimizations that G1 invalidates.
I'll look in.
Okay, sure. Send me an email. I would love to start a dialogue. I am not a I'm not a compiler expert. I'm not a C2 expert. I'm doing my best to try and work my way through and make sure that this simple little, one line of code that I want, the right barrier hooks are already there. The simple one line of code that I want to get executed on all reads gets put in place. That's where I am. Okay, are there any other questions? Yes?
How much complexity is caused by the fact that you have a language with a thread-based shared memory model rather than, say, a message passing language where you know which objects are associated with which threads?
I don't know how to answer that. All of the work I've done in garbage collection has been in either Lisp machines or JVMs with a shared memory model. Distributed garbage collection is harder. I know that it's harder. I know that finding cycles is harder. I know that any kind of stop the world phase in a distributed garbage collector is 10 times more expensive than it is in a shared memory model, but I've never done one. Any more questions? Are we done? I guess we're done. Thank you so much for listening to me.